The subject of this video is called the Doppler effect. Doppler effect is the relative shift in the frequency depending on the motion of the source and the observer. You sometimes have noticed that when a fire engine or fire truck comes toward you, the frequency of the sound seems to increase, and then when it gets away from you, the frequency seems to decrease. So it's that apparent frequency shift. It's very real, but it's not really happening in the at the fire engine level. It's only happening at your hearing level. So that's that shift in frequency that's called the Doppler effect. Many creatures in nature, such as dolphins and bats, use the Doppler effect using echolocation. So it's a pretty important way to navigate if things like photons are not an option. So let's try to understand the theory behind the Doppler effect. The main thing we have to conserve in the Doppler effect is the number of wavelengths between the source and the observer. From the viewpoint of the source and from the viewpoint of the observer, the number of wavelengths that you're counting must remain the same. They may get compressed, but the number should remain the same. The wave number is given by this quantity k, so that's 2 pi by lambda, and that should be the same for the listener and for the source. So I'll write this equation: 1 over lambda listener equals 1 over lambda source. Now lambda is given by speed over frequency from the wave relation, because lambda times frequency is the speed. So if you're going to cram a certain number of wavelengths between the source and the observer from the listener's point of view, then that equation there for the listener is going to be FL over the speed of sound. That's really what the speed is, but relative to the observer. So it's going to be V plus or minus the frequency of the speed of the listener. And here I'm going to say, by the same reasoning, it's going to be the frequency of the source divided by the speed of sound plus or minus the speed of the source. So S here stands for the source of the sound, and L stands for the listener of the sound. Let's try to see how this plus or minus works here. The plus or minus is there so to take into account all possibilities. So there are really 4 possibilities and not any more. So let's consider those 4 possibilities and find out what signs to use for each of them. The first one is where the source is chasing the listener. So there's a speed and the listener is moving away. So think of this as a police car that's chasing you. What are you going to be hearing in terms of the frequency? Well, first of all, the best way to do these problems is to imagine that you are not moving. If you're not moving, you're going to hear the maximum effect. So that would be, if you're not moving, VL is 0. So I'll write this as FL over V being the speed of sound, is equal to Fs. Now you're going to hear a higher frequency because the waves are getting crammed together. So the wavelength is decreasing, so the frequency must increase. How do you make the frequency increase? You have to have V minus Vs here to make the frequency increase, because then I'll get FL equals V divided by V minus Vs times Fs. Now what if you're getting away? That was for when you were not moving, but you're getting away. So that's going to be reduced a little bit, even further. So now the correct formula is V minus VL divided by V minus Vs. So that's one case. The other cases are very similar, but I'll do them anyway for the sake of completeness. And you'll see the pattern emerging on how to choose these signs. So the second case would be where you have, well, let's see. Now the source is coming towards the listener. So this is the case where a fire engine comes towards you and you yourself are driving on the street to face the fire engine. So let's assume again you're not moving. If you're not moving, then you're back to the same expression here. So the first level of attack is assume that you're not moving, so the listener speed is 0, and then you're going to hear a higher frequency because it's coming toward you. And now you are moving, so this effect's going to be even greater. So the sign you will choose for this one is going to be V plus VL divided by, this is if VL is equal to 0, and that is if VL is not equal to 0. It's always better to do the elementary case first to see what sign to choose for the denominator, and then fix the sign of the numerator accordingly. Okay, there are two more cases, and you can probably guess what they are. So now we have done the source going to the right, so all we have to do is change the sign here. Source is going to the left, and the listener is going to the right. So here, again, assume the listener is not moving, then the source is getting away from them, the wavelengths are getting stretched, so the frequency must decrease. So let's do that problem first. VFL divided by V equals Fs divided by V plus Vs. That will ensure that the frequency is going to be less. Now, the frequency is going to be even less because you're actually getting away from it. So the only way to make it even lesser than what you have is to put a minus sign in the numerator. And the last case is where the source goes to the left and the listener also goes to the left. Now you may think, how is this any different than that? Well, the difference is that the source is the one that's making the sound. So imagine again the listener is not moving. If the listener is not moving, we're back to this. So FL over V equals Fs over V plus Vs. So he's going to hear smaller sound, less frequency. And now he's chasing it. Well, if you're chasing it, you're kind of compensating for the fact that it's getting away, so the frequency is going to be a little bit more than this. So the only way to make it a little bit more is to write it as V plus VL over V minus Vs times Fs. And that's for the case where the listeners are actually moving. So we have covered in this manner, just using some basic common sense, we have covered all four cases, and that's what the plus or minus really means in the Doppler effect. It's to cover all these four possibilities. Let's actually solve a concrete example, one that you might have encountered in your real life. So I'll take this example of a train. So you're in a commuter train. And there is a railroad crossing. Okay, there's a railroad crossing. And the railroad crossing, as you know, makes this ding, ding, ding sound because it needs to alert people that there's a train coming. Well, let's assume that you don't know how fast your train is moving. Your train is moving at some speed, which I'll call VL because you're going to be the listener here. But you don't know how fast it is. That's one of the things that you're trying to find out. But you do know the standard frequency emitted by all these railroad signals. Let's suppose that you just looked it up online and you found out what that is. I claim if you have an app that can measure the frequency of this as heard by the app or you can actually figure out the speed of the train. So let's assume that while the train is coming towards the source is S, the railroad signal, you're going to be hearing a frequency which I'll call F1. And now when the train has passed the signal is still going to sound for some time because they usually like to wait for the train to go away a little bit before stopping. So you can still measure with the app some frequency F2. Now usually F1 is going to be bigger than Fs. If your train is having a positive velocity, it's going to be bigger than Fs. So let's call this alpha 1 times F, where alpha 1 is bigger than 1. And F2 is going to be smaller than Fs because you're getting away from the source. So that's going to be alpha 2 times F, Fs, which I'm just going to call F for simplicity. So this is alpha 2 is less than 1. So that's the facts of your experiment here. All right, so you're trying to find the speed of the train, and let's assume the train does not speed up. It's just the same speed throughout. Okay, now this is the case of the listener coming towards a source which is not moving. So he has to, the listener, that's you have to be hearing a bigger frequency. So use this formula, FL divided by what will give us that. Suppose you're not moving, then of course there's nothing to do. So you have to assume that you're moving in this instance. It's going to be V plus VL should be equal to Fs divided by V. The reason is Fs is not moving. The railroad signal is not going any place. So you cannot put any speed there. The only way to make your FL bigger than Fs is to have V plus VL here. So I'm going to get FL equals V plus VL divided by V times Fs. Now for this stage, so I'll call this F1. What about F2? It's opposite. You're going to have V minus VL equals Fs divided by V. So F2 will be V minus VL divided by V times Fs. Actually, it turns out you don't even need to look it up to find out what Fs is. All you need to do is measure the frequencies F1 and F2 using your app. And now what I'll do is I'll divide the two. Dividing gets rid of a lot of things. So F1 over F2 is just going to be V plus VL divided by V minus VL. I've already said that F1 is alpha 1 times F and F2 is alpha 2 times F. So that's where I claimed that you don't really need to know the standard railroad signal frequency at all. And let me just call alpha 1 over alpha 2 beta to deal with this arithmetic here. So I'm going to get V plus VL equals beta times V minus beta times VL. VL is the speed of the train, by the way, because you are inside the train. Let me take beta times VL to this side and V to that side. So I'm going to get 1 plus beta times VL equals beta minus 1 times V. So I have the speed of the train. It is beta minus 1 over beta plus 1 times the speed of sound, whatever the speed of sound is. So if it's 343 meters per second, you actually have a formula for the speed of your train. So V train, let me put what beta is. Beta was alpha 1 over alpha 2. So that will be alpha 1 minus alpha 2 divided by alpha 1 plus alpha 2 times the speed of sound. So that's a really neat way to find the speed of sound, speed of your train. Or if you know the speed of train, you can actually use this to find the speed of sound. I didn't realize this was also a good way to find the speed of sound. You can absolutely turn it around and solve for speed of sound in terms of the speed of the train, or you can just find the speed of your train. Okay, so that's one concrete application of the Doppler effect. The Doppler effect is also used in many other areas. One possibility of the Doppler effect is weather forecasting. So if you imagine this not to be a train but a cloud of rain, then the station that's the weather radar station is going to constantly be sending out a radio wave which bounces off the cloud. So now you're going to have two Doppler shifts. So the wave is going to reach the cloud, and once it bounces off the cloud is going to function as a new source of those waves. And then by detecting the ratio of the two frequencies, what they sent out versus what they received, they can figure out how quickly the cloud's coming and how soon there's going to be rain over Rochester or Canandaigua. So you can do weather forecasting. Another place where Doppler effect is used is to figure out what's there inside your body. Suppose you have a cyst or pregnancy or anything like that. What you do is you use the ultrasound, and the principle is the same. Those sound frequencies are shifted in frequency when it comes back to the machine, and based on that they can figure out things like the fetal heartbeat, and if you have a tumor, then the tumor size can be deduced. So it's a very useful technique in medicine.